what is important is the concavity of this function. That's the risk-adverse individual, because under the logarithmic we have concavity. And then we have an alternative guy, and this one is going to be risk neutral. We know that is risk neutral because of the linearity of the function. So the guy that is linear will look just to the expected value. Whatever it has great expected value, A, B, C, is going to be the preferred option for that guy. But for the risk-adverse individual, things are more complicated. It's not just expected value. It's expected value, and that's corrected with the second derivative of the utility function, and that's corrected with the variability. That introduces a different set of preferences. So let's take a look at that using Excel. Okay, I'm gonna go up here, and this is gonna be the risk-adverse guy. That's the most representative one. And I'm gonna put the payoff, and that's gonna be 2, 5, 8, 20.
Where is that the Excel file?
It's not this file. I'm working on that from scratch. This one is that's workshop. We are working together. So also feel free to follow your own path and just sort of accommodate in mind, and just like that. 820. So 8 goes here. 20. 80. And 100. This is the value taken by the random variable. I'm going to take an auxiliary thing. So this is going to be log payoff, right? Which is the utility evaluated in these points. So that's very simple. Natural logarithm. Take care with that. Some languages, for instance, MATLAB uses the American notation. Log means natural logarithm. Excel distinguishes. Natural logarithm is one option, and another option is something that we never use in economics. The log, the logarithm in decimal base. We never use this. We have natural logarithm. So natural logarithm of 2 is going to be 0.69, and then I copy paste to the right, right? All these formulas, and that give us the log payoff. This is going to be the utility. And then I'm going to take an auxiliary step, which is log payoff squared. It's not clear right now why I'm going to do that, but it will be clear later. When we are required to compute the expected value and the variance. And I need the expected value squared to compute the variance, okay? So we have the payoff, which is the information that comes in the table. Then I'm using the logarithm. And I'm going to use logarithm squared. And logarithm squared goes just like a logarithm. To a square we use this hat. Somewhere in your keyboard, depending on Spanish, it's going to the right, but depending on other languages, maybe in other keys. So this is what you need to look for, and that is squares. Okay, but utility square. Not apparently, it's not apparent why we want that at this moment, but it will be clear later. All right. And then we have all those probabilities. A, B, C, right? A, B, C. So it's gonna take us seconds, but it's very easy, right? 0.20, 0, 0.35, 0.15, 0.25, and 5%. For B, 0.05. Thus, we can copy paste those in 50%, 20%, and 15%. And just one more, 10%, 20%, 0, 20, 40, and 10%. If everything is right, I'm just going to check that everything is right using the sum command. Sum makes the sum of all those probabilities, and of course, if everything's fine, all these columns you need to up to see, I made an error here. 10, 20, 0, 20, 40, and 10%. Oh yeah, see. Always double checking pace, always. Small control, but now we are good. All right, so what is the expected utility? Right? For A, B, and C. Expected utility of A is these values times these values here. Right? We are right. Is this value times this value plus this value times this value plus this value, right? So we need this cross product. Excel knows that a very common function that very often appears is this cross product operation. So we're going to take advantage of an Excel function that is called sum product. It can be done in very different ways, but we want to do it very easily. We don't want to, this times that one, this. So I'm going to use a special function in Excel which is intended to do that. It takes two arguments, two arrays. Array 1, so that's going to be my my log utility function, right? And then I have semicolon in Spanish because this is Spanish. So you have the semicolon. You may have comma if you are using other languages. Watch out that. And then we feed with the probabilities. Same dimension, you see. So Excel understands that we want to take one array and do the cross product automatically. I'm going to use a copy paste later. So I want to do what is called lockdown. I want to do an absolute reference. Well, let me do it first. Let's make sure of what is the expected value, right? So if I hit, the expected utility of A will be 2.64. The units of the expected utility makes no sense. What is the interpretation of the 2.64? I don't care. That's not what the utility function is meant for. The utility function is just to make comparisons or the ordinal rankings. If B gives me more utility than A, B is preferred to A. Stop. Period. No more analysis. So 2.64 units means nothing to me. I want to do the same operation here. So we can take advantage of the Excel structure by copy pasting down. But if I just copy paste down like this, then the references take the probabilities of B, which were fine, but we see that Excel has moved the two ranges. I'm fine with the probability, but I want to fix the call to line 4 where the log utility function is. So what we need to do is to lock down that reference to make what in Excel is called an absolute reference.
Can you explain the sum product?
Yeah, some product, it has just two inputs. The first input is an array. It can be a row or it can be a column. So the first column, B4 to G4, the first array, is telling Excel, I want to do something with these particular cells. And then the second input is another array of the same dimension. So that was, let's say, a 1 by 6 row vector. This is another 1 by 6 row vector. And some product takes this guy and multiplies it by this guy, plus this times this, plus this times this. So it's doing the sum of it's called the inner product of two vectors. Okay? And it's making exactly the operation that we want to do. Taking this cross product across the dimension of the array. So, because we want to take advantage and copy paste it, this of course is a possibility. You may do that in your own way. But the most efficient way to solve this problem is taking advantage of this function and of the possibilities that Excel offers. So I'm gonna lock the range B4 to J4. Right now it's called a variable reference. I want to do an absolute reference, lock in this range. So I go to B4 and I press key F4. If you have the laptop, you may have to press the Fn, something that is there in your laptop because you have multiple functionalities in the keys. So you want to activate something which is not necessarily F4, and you may see F4 written in small blue letters or something like that, and you need to press Fn. Here, because I have a kind of big keyboard, all the keys have its own function. So in Excel is F4. I press F4 and this happens. I had used these $2 to lock in this value. And then I go to J4 and I press F4 again and I lock in this range again. Now I'm letting Excel copy paste this range. Whatever you do with this range, this must be preserved. So you copy paste down, as we did before. If I copy paste down one level, the reference to A has been updated, but the reference to where the log utility was is preserved. So that's perfect. That's what I want. And then I can copy paste down another level, right? And we see that that operation is preserved. It's a very important thing and a very super useful thing to know when to lock in and when to not. In general terms, it's a good idea to lock in, but you need to be aware what you are doing. Okay? So the decision for this guy, this is a for Newman maximizer. So he has three options, and for this guy, it's very simple. He goes to option B because B is the one that gives greater expected utility. Okay, I'm gonna put it here. That was the Visa version. And then I'm gonna make the comparison. I'm gonna put it right away. I'm just interested in this guy. In this guy, there is neutral. For this neutral guy, the decision, the utility, because the utility is the same as the payoff, the utility is just the payoff, right? We all agree. You just take the payoff, that's what matters for him. He cares about nothing else. So we're gonna repeat this neutral utility by taking the multiplication, the sum product of the payoff right away. I'm gonna lock in B3 and G3 already. And now for lottery A, we take the probabilities for lottery A. Okay? Take a look, take your time guys, feel comfortable, but the operation that we are doing is exactly the same as we did before.
¿Cuál es la manera rápida de hacerlo en dólar?
F4. It's super important. Fn, but because you may have, watch out because you may need to press Fn at the same time because you are calling this thing in the laptop. Those keys are taking multiple functions, so you need to activate the Fn. Okay.
Why did we put B like red?
It was me, just to
but-
emphasize that this is the one that maximizes.
Okay.
Okay.
Yeah, it's the highest.
Alright, and now for the neutral guy, the same thing, but the preference is different. This guy is a different guy. They both are different people. They are confronted with the same decisions, involving the same assets, but their local preferences, their subjective preferences are different. So their decisions may be different. And they are doing the same thing. Each one is maximizing expected utility. One will look just to the expected payoff, that's the risk neutral guy, and the other is the one that sort of captures the way we mathematically, of course, it's a model, but captures how most people in the room here will react. So again, units are, the comparison in terms of units is meaningless. What is this 31.2? Nothing, forget about it. The interesting thing is when you take this and copy paste down. 41 is preferred to 31, 47 is preferred to 41. So C is the one that he prefers. This guy there is neutral guy prefers decision C. He's happy with C. This averse guy is happy with B. Each one is making a rational decision according to their preferences. But of course, you see how that changes. One prefers B, one prefers C. They both are von Neumann maximizers. B will sympathize with B. We understand the world as he does. Okay? So just one final exercise here, which is variance. We have computed mean, and now we need to compute the variance of a discrete random variable. I'm going to take advantage of the fact that the variance of a random variable x is the expectation, right, of x minus the expected value of x, and all that squared. That's the formal definition of variance. But if I sort of stretch that idea, this turns out to be the expected value of x squared, so second order moment, as we define it in class, second order moment minus the expected value of x squared. And we know by Jensen's inequality that this is going to be positive. What we discussed, x squared is a convex function. Well, then for a convex function, the expected value of the square is greater than the square of the expected value. We use that in the concave world. In the concave world, that would be less than. In the the convex world, which is the mirror space, everything is reverted. So this, by the Jensen inequality, the expected value of the x squared is greater than the square of the expected value. We know the expected value. For A, B, C, we have it here. So now for the risk neutral guy, I'm going to take this over there. I'm going to put expected value of x squared. Okay, this is an auxiliary thing for me. A, B, and C. So, the expected value of x squared will be those square values of the utility function weighted by the probabilities. It's not the expected value of x squared is not squaring probabilities. The probabilities in the moments are always used as the weighting, as the weighters, as the weight. We just square the values taken by the random variable. So the expected value of x squared is the sum product of these squares, right? We log the dice, and then we use the probabilities. If I use the probabilities of decision A or lottery A in the words of von Neumann, then that's the second order moment of this thing. 100, it takes values like 100, which are very high. Sorry, 21, which is very high, but it's kind of down-weighted by a low probability. So it gives us 8.81. Because I use the log, now it's safe to copy paste down, and we have those squares. So, the variance of the log utility of A, B, C is nothing plus the expectation of S squared, expectation of the log utility, minus the expected utility squared. That's the variance.
Sorry, could you come again with that one?
So we have expected utility first, right? Then we have just computed the expectation of x squared. The variance of x, it can be expressed as the expectation of x squared minus the expectation of x squared. So I'm doing that operation manually to compute the variance of a discrete random variable. And that gives us variance 1.83, 1.89, 1.89, 1.09, 1.89. That's why there is neutral guy and there is adverse guy sort of have an argument here. Yeah, there is more expected value in decision B, but C is also more risky. You see? C, he perceives a lot of dispersion in decision C. There is less dispersion in decision B. He goes for B. He penalizes in his decision. He sort of trades off expected value. He likes expected value, but he dislikes variance. So in the utility function, in the concave utility function, the trade-off is solved in favor of B. B may have less expectation, B has less expected value than C, but in terms of utility, there is less variance involved. So the reserve guy, looks not just for the expected value of the game, sort of penalizes in terms of the variance. This is the variance. If we take the square root, okay, we take the square root, that's the standard deviation, the volatility. So he likes B because it has greater mean and smaller variance. Yep. So Maria.
Could you show the formula with the expect? Yeah, that formula.
Why? Why do you?
okay, the log peri of a square makes only sense. I use that only for the variance. Just in order to give us insight why this guy is going for B when C has a greater expected value, right? C has a greater expected value, hence a guy that just look at the peri of itself will naturally go for C. And the answer is he goes for B because the utility function internally, the log utility function through the concavity has taken into account that C, which has greater expected value, is also the more volatile. So going for C increases the variance, and that's something that dislikes the resolver's guy. So he makes a different, the optimal decision is over. Okay, understood, guys?
You show the function of possibly 5 sources.
3.3
One.
The column next to the variance of the log of
column 7. This is
Sorry,
D
D19.
D19.
Sorry.
Square root.
Sorry.
Sorry, that's one point. That's variance. Okay, let me put it this way. That's the variance. And that would be the standard deviation of the natural logarithm. I remember that I use this long notation. I'm so used to that it takes a constant effort not to put that's by log in this course. That's what I said the first day. I mean always natural logarithm. Okay, so this is we see that he's taking something that is sort of minimizing variance. And of course, according to the preferences, variance is a problem. Alright, guys? Questions? Okay, so let's move to the third workshop that we skipped, which is more interesting because I'm going to introduce Monte Carlo simulation here. Some problems are hard to solve because we have those nonlinear functions, a natural logarithm. Yeah, when I have this discrete random variable, it was kind of okay, but what is the expected value of the natural logarithm is much more complicated. So we use a lot of Monte Carlo to solve complicated problems. What we're going to do is believe that we have an individual that has an initial wealth or 1,000 euros. This guy is happy with his initial wealth. Now, someone proposes a fair game based on a single draw from a normal distribution with mean 0, so that's a fair game, 0 mean, remember, and a variance which is 200 squared. Variance needs to be parameterized in these terms. The normal, whenever we say something is normal, we use this notation. Normal with mean mu, variance sigma squared. So I emphasize this idea, saying standard deviation is going to be 200, variance is 200 squared. This guy will be unhappy with this. This guy, because he has if this guy has a logarithmic utility, a concave utility function, he is going to dislike the idea of being shocked, even if the shock has 0 mean, meaning you may gain or you may lose, yeah, but I'm better off not taking this gain because I dislike the variance. And you are selling my wealth to variance that we saw before is something that I dislike. So I'm better off not taking the gain. We're going to see that through Monte Carlo simulation because we know certain magnitudes, but determining the value of those magnitudes can be complicated. So we want the expected utility if the individual assess the gain. Alright, expected utility involves the expectation of a logarithm of a normal. That's complicated. So we're going to resort to Monte Carlo simulation to compute this expectation. How are we going to do that? Pure brute force exercise. I'm going to generate, let's say, 1,000 tries of a normal distribution. I'm going to check the utility function of his wealth 1,000 times. On average, that's expectation. That's what expectation means. On average, what happens to you? I'm going to do that using Monte Carlo simulation. Then, Pratt's risk premium. He dislikes the idea of being shocked. How much will he be willing to take in order to remove this shock? He will dislike the idea of being shocked. He's going to end up with less expected utility. All right. How much he will be willing to pay to avoid the shock. And the certainty equivalent. How much wealth is going to have after paying the certainty equivalent. All right, let me take this information. I'm going to make a screenshot. I go here, and now I click and stay in the cell file. Alright, so first of all, in a Monte Carlo simulation, we want things to do to be automatic and to select things. That's the game. So I'm going to put here what we call drivers. In this type of experimentation, our experiment is given by certain variables, right? So we can identify, for instance, initial weight. Yeah, the guy has 1,000. But what are, because everything is going to be sort of moving, we're not allowing the guy to have any other wealth that I may change. So I'm going to give it as a driver. So initial wealth, 1,000 euros. I'm putting it like that. I'm going to use the coin symbol up here, right? To emphasize this 1,000 as number. Initial wealth, 1,000. So like I said, my point is, I may write 1,000, but if I make references to B3, and then I will be able to change B3, and my exercise will be much more complete. This Word file would be much more useful, allowing me to change anything that I want. Then we have the shop. The shop, by construction, by definition, has 0 meaning. 0 euros, of course. So 0 goes. But I may like to change that. What if I want to show this guy with something that is, for instance, 100 euros? He will like in that game. What if it is something like a minus 300? Then his premium will be greater because he needs to move away from that expectation plus the variability of the fair game. And then we have the standard deviation. That was 200, right? Yeah, that's what we said. Standard deviation, 200. Remember, standard deviation 200, variance 200 squared. All right. So this exercise is very simple. We don't have nothing much more sophisticated. The drivers in my Monte Carlo analysis is just 3 values, and we may change those values in will. Let's do 1,000 simulations. So I'm gonna say simulation. Now there is in the last versions of this was introduced like 3 years ago. There is this function sequence. You type sequence 1,000, and we'll make this thing. Automatically, it's print a sequence of values 1, 2, 3, 4, 5, 6, blah blah blah, all the way up to 1,000. Okay? Control, down key, control, shift, down key, and I select all this range. You see that we end up at 1,000. And I'm gonna make it look nicer by using the center. Okay, I'm gonna justify this thing. Simulation has this form, alright? And I move with those control keys, right? Control down, I go down, control up, all the way up, control, shift, down, I select the whole range. That's why I put all this.
You said the formula sequence, right?
Huh?
The formula sequence.
The formula sequence, and that has been auto-filled. It depends on the version. If you don't have that, you will have to do that manually.
Yeah, I was gonna say there's
It's not a big problem though, right? Okay. So now we wanted to generate the shock.
0.
No,
It's mean 0.
it's mean 0. Exactly, it's not the same. Okay, so I'm gonna use one of the functions in Excel, which is norm in. Norm in is a function, is called, the technical name is quantile function. The quantile function, the typical exercise in probability that you remember is you give me one value, let's say for instance, if this is the normal distribution, you ask me for this value, so let's say something like, for instance, -1, right? That will be 0. You ask me for -1, and then the question is, what is the probability of my random variable not being greater than -1? And the answer is, you need to integrate the density of the normal distribution to get this probability associated to that point. Okay? The quantile function does exactly the opposite job. You let me know the probability, and I need a special software to solve a highly nonlinear equation that will be this one. I need to find the value x such that when we integrate the density function, gives me that probability that you are feeling. Normal exercise that you remember from your courses in statistics in the undergrad is I give you a value, what is the probability associated to that value? Give it, turn that problem, give it the right. I give you the probability, what is the value related to that particular thing. And you need to solve an equation which is implemented in Excel by the name of norm_inf. So norm_inf has 3 ingredients: probability, mean, and standard deviation. So probability is random. We are on a field with a random number. I'm putting that inside of the function right away. Remember the other day, I have a columns with the random numbers. Now I'm feeding that automatically. That's going to be an input automatically generated, and anytime we refresh, it's going to be generated. Then the mean of the shock, we have it at default. Because I want to copy paste down, this guy needs to be logged as with reference to the mean, and then Excel is asking for the standard deviation. This is very important. When you do simulation with different softwares, the normal distribution can be characterized by either standard deviation or the variance. Some software will ask the standard deviation, like Excel. Other may ask for the variance. So we need to be aware. Excel is asking for the standard deviation, and the standard deviation is what we have at B5. So B5 is log F4, we log it. Close parenthesis, hit enter, and now we are shocking with a random amount that this guy dislikes. 166. This is good for him. I'm saying I will give you 166 in this simulation, in this trial. If I press F9, by pressing F9, the Excel file is going to be refreshed, and we are creating new shocks. Now you're not so lucky. Now you lose €7. Now you gain 156. Now 166. Now you lose 137. You see the idea? Okay? Anytime I press F9, anytime I do something in this workbook, this is refreshed and a new random draw is automatically created. So we have a model. This is an economic model. This is financial modeling. We are using Excel to replicate something. This guy is going to be confronted 1,000 times with 1,000 shocks. And we are going to sort of learn what happens to that guy by examining on average situations. Alright, because we have created the simulation column, so we have something to the left. Excel knows where the ranges start and where the ranging ends up. So I'm gonna go to the bottom down corner, right? See the shape of the mouse. When I go to the bottom down corner, shape changes, double click. And this is copy paste down. I have 1,000 simulations of the wealth of that guy. And this is of course normal distributed. If I take shock, Control Shift down key, we select all those values and we go to insert, recommend chart. We have the histogram of the wealth of that guy. Let me take this thing, okay? I will repeat in a second. Just let me put it up there. This is the shock to the wealth of this guy. Random shocks, and anytime we press F9, we are creating an entire new collection, a new entire Monte Carlo simulation. But of course, the main features are controlled by the normal distribution. It's a Gaussian distribution, center at 0, having a standard deviation of 200. Okay? Now, this guy has now wealth. Wealth was the initial wealth, 1,000. So I press F4 to block the initial wealth, plus the shock. You had 1,000, now you have 1,000 plus 138. You are happier this time. Yep. What we have here is just wealth plus shock. So this is where you are now. You started 1,000, and that's where you are now. This time, next time 988, and then we copy paste. That's your wealth.
Sorry, can you repeat that last first piece again?
Yes,
So wealth is
1,000 plus shock.
plus.
You started with 1,000 in this first time. It's like we have 1,000 individuals,
Right.
and this first guy was very unlucky. He lost 100 euros. The second guy was unlucky as well, but lost only 74 euros. The third guy made 242. He was happier. This is happier. So we are learning from this scheme, okay?
Perdón, what's the difference between Monte Carlo and quasi Monte Carlo simulation?
Pseudo Monte Carlo simulation. Because these random shocks are not really random. So all we do here with computers, even though we say Monte Carlo simulation, it's understood that in reality it's pseudo Monte Carlo simulation. It's always pseudo Monte Carlo simulation. Not everyone agrees with that, not everyone is aware of that, but no computer can generate truly Monte Carlo space.
Yeah, I read that in before.
It doesn't matter to us, it's not a critical difference, but just important to know what you are doing. This is pseudo Monte Carlo simulation. Alright, and then
One question, why if I insert a value next to that cell, no, next, sorry, the blank cell, put a value please.
we then,
Can you write a value, like whatever value?
yeah, I'm gonna put here the utility, right? That's gonna be the utility of wealth. So I'm gonna write here the natural logarithm of wealth.
No, but I mean that when I write a value next to that cell, the values of the columns change.
Everything's changing, everything is refreshed. Anytime you do something, because of the random function, is making everything change.
And if I don't want,
You need to copy paste and fix the values, and then you will not have truly Monte Carlo. It will be that particular illustration. This is Monte Carlo. In the homework, this is what I want. I want to be able to refresh. If I press F9,
every time that
I will change the values, and I will know. I'm interested in your ability to make the model, not just some values. So this thing that you see like exactly is what I like. Anytime we do something, everything is changing. So of course, I can just say, now, right now it's 987. Soon as I do something, this is gone. So that's why we need to say some things in terms of averages. And this error, anytime you create something, it's like a drawing a new 1,000 guys and learning from them. So on average, you will get the picture. This is what I want. I'm totally happy with this.
The shock, the example.
The shock? Okay, the first one is the probability. So run with empty parentheses. Then mean, and this is log, and it's very important to log it. Otherwise, it's going to be copy paste down, and you will create errors. And standard deviation log. run doesn't need to be locked, but the other arguments, they need. Okay, and then we have the utility, 6.78, we copy paste down, and that's utility. Utility is gonna be a random, it's gonna be normal distributed, what do you think? Before doing that, how is gonna be the utility? It's gonna be normal distributed?
It should, right? Because they're identically and independently distributed, because
Wealth.
it's just
Wealth is normally distributed. Wealth is normally distributed, but utility is normally distributed.
No, it's not.
It will be unknown.
It's gonna be normally distributed. It's skewed. It's not normally distributed because the unlinear transformation, any linear function of a normal distribution is normal. But this is not a linear function, that's a logarithmic function. Then you lose normality. If we see how the utility function looks like, the distribution of the utility function looks like, this is not normal distributed, it's skewed. Okay, shocks are normal, wealth is final wealth is normal, but utility is not normal. Okay, let's compute things then. So initial, final. No, not like this. I prefer this. I prefer this. Let's say that it's neutral. And let's say there is adverse. So the log, right? The log guy, okay? So we have initial utility. For this guy, for there is neutral, because we have 1,000, there is neutral, utility is just what you have, right? 1,000 is neutral, is a guy for which the utility function is just x. And there is adverse, is a utility, is a guy, right, for which the utility function is the natural logarithm of x. So the initial utility of a guy having 1,000 is 1,000. But please note that in a financial model with Excel, we should not write 1,000, but making the reference. Because if then we later change 1,000, then we should fill all the references necessary. I'm not typing 1,000, that would be a mistake. I'm making the reference to 1,000. And there is a adverse guy has the natural logarithm of 1,000. Of course, you may say, oh, the guy with 1,000 is happier than the guy with 6.90. That's not correct. The utility function is not used in that way. It can be only used in order to run preferences. You cannot say this guy is happier than that guy because the set of preferences are different. You cannot make this comparison, okay? Now,
So what is the formula again for the risk first?
Log of 1,000.
expected utility. The expected utility of a guy having 1,000, when we shock it randomly, is 1,000. That's why this guy will be okay with this game. If you bring me something that on average has 0 mean, on average does not change my wealth, on average does not change my utility, I'm okay with that. I don't care, I don't feel anything wrong with this game I'm not particularly interested neither. Right? So it should be, let me put it to be more exact, this thing plus the mean of the shock. If the mean of the shock is 0, nothing changes. This guy has the same utility. And now we have a problem. I need to compute the expectation of the utility, which is non-normal. So it's not like this guy is going to be 1,000 plus blah blah blah. So in order to compute the expected utility, we take advantage of Monte Carlo simulation. I'm going to say that's the average of your simulation. You have this column with simulated wealth. You want to see how, on average, that guy looks like. Okay, do it. And what you're going to observe, typically, is this picture. This guy is less happy than he was. So I press F9, and we will see that coming systematically, right? Well, systematically. Sometimes it's random simulation, sometimes, right? You have that loss, even though the expected wealth is the same, right? Expected wealth is 1,000 plus 0, even though the expected wealth does not change. The expected utility does not change for this neutral guy. It tends to be smaller because of the concavity of the utility function for the risk adverse guy. And press F9 as much as you want. You will see that in the simulations coming and coming over and over. Okay, risk premium.
Sorry, how do you calculate expected wealth?
Roberto,
Yes,
how would you do that?
I think doing the same we did with utility but with the wealth.
The expected wealth, you had 1,000,
Yes.
then you shock, the shock has a mean. So the expected wealth is what you have plus the average of the shock. So that's how I'm feeding the model. I'm saying 1,000 plus the average of the shock. I'm making this reference. I know it's 0, but what if you later want to change that and rather than 0 put another value? So you make the reference. You change 100, that's not the amount of change. Okay? Jack, should be more
So you're using the same formula for expected utility as expected wealth?
expected wealth does not change, but expected utility does change.
No, but for the risk neutral,
This one?
not for the left, the G8. Yeah.
G8.
So this
Yeah.
is,
Yeah, because for him utility is wealth. He's a risk neutral guy. He just cares about wealth. So that's why he's okay with that random shock. It's not a bad thing, nor a good thing. I'm okay. I feel indifference. So it's not changing my expectation.
so in that sense, expected utility and expected wealth have the same formula, right?
They have literally the same form. This neutral guy cares only about wealth.
And then for the expected wealth of the risk adverse, the
It's
age.
1,000. Expected wealth is fair game for both the risk neutral and the risk adverse. It's changing the utility dimension. This is not fair game anymore. This is fair game in the wealth and in utility. It's not fair game anymore in terms of utility for the risk adverse because of the concavity of the utility function.
And then geograph referencing G9, right? On the 1,000 that's below. That one you're referencing.
Because it's not changing. It's the same value, does not change. So 2 more questions, guys, and we are done. We are done. Risk premium. Price risk premium. Uncertainty equivalent. The easiest guy is always the risk neutral guy. Perhaps risk premium for the risk neutral guide. Certainty equivalent is the same the amount that is the expected wealth, right?
Is 1,000.
It's 1,000. So perhaps risk premium is the difference between the certainty equivalent is the expected, let me put it there, is expected wealth minus certainty equivalent, so it's 0. He does not require a premium. He will not give up his shot. Certainty equivalent for the risk adverse gap. That's tricky. But we are smart people. How we compute the certainty equivalent? Is the value that gives you the same expected utility of the game.
Expected wealth times wealth that risk premium.
The exponent of the expected utility.
Do we all agree? Victor, explain.
You see, we have the expected utility in yes, that one. So for us to get that is in log terms, so the certainty equivalent is the exponent of that because we are using logs.
We are asking for the value that gives you the same utility that we are getting on average, the same expected utility, right? That was the definition of the certainty equivalent. The utility evaluated at the certainty equivalent gives you the same as the expected utility of your game. We know this. The expected utility of the game is this 6.89. We are asking for the value that when it's plugged in utility, and utility is the natural logarithm. The natural logarithm of x needs to be equal to that expected value. So like Victor correctly points out, we take the exponential to undo the logarithm. And then you get the certainty equivalent. So if I go to the certainty equivalent and we type the exponential of this expected utility, this is going to be a value which is smaller than the initial wealth. So he had 1,000. That means, let me put it here, this minus this is what he's willing to pay. This is the Bratz risk equity premium. You see that? Look the configuration right now. This adverse guy has expected utility which is 6.88. See, he had 6.90. The value that matches 6.88 true is 976. He had 1,000. So that difference is 23 euros. This guy dislikes this game because it shocks his wealth, and he's willing to pay 23 euros to get away from the shock. Up to 23 euros. Because that point, which is losing money, you say, why are you okay with losing money? Because this is the feeling, this is exactly how it feels playing the game. He has the same expected utility if he's forced to play the game, or if he loses right away 23 euros for sure. That's the equity risk premium, and that's the symptom of risk aversion. He's willing to pay because playing the fair game feels like a loss.
Can you show one more time where you're using exponents on certainty equivalent?
Victor, that was your idea. Explain, Alex, why you are using the exponential.
So if you have a number, for example, if you have the 12th column, you see that column? If we move from column C to column D, we take the ln, right? So if you want to move from column D to column C, what do?
Oh, you reverse
reverse.
Okay.
The log and the exponential are the inverse function, the one of the other. So you want to solve essentially an equation in which you have log x equal to certain number, c, whatever is in the, so you solve x by taking the exponential of c. That's what Victor smartly solved very quick. More questions, guys, because that was the workshop. Two things here to take away from this. First of all, Monte Carlo simulation. I'm going to request you to do Monte Carlo simulation because this is for us in finance. You see how easily things can be sort of crafted in order to get insight on the dynamics. You ask me, what is the expectation of a logarithmic function of the normal shock? It's like, oh, wow, I don't know, man. Probably it has a closed form solution in one of those books. Let me check. It has a closed form solution, but I cannot remember. But if I do this with Monte Carlo simulation, I know that that expectation can be approximated with a very large number of observations. That's the only requirement. If you do Monte Carlo, you need to do big numbers, 1,000 simulations. But what is the problem? When it was a PhD, that would have been a big problem. We didn't have computers. Laptop is something that I saw first time. I still remember the first time I saw a laptop. It was a luxury item. I remember a professor with a old professor. He was so super proud. Look at what I have bought with a project. And we were like, oh my God, a laptop. And see right now, guys, everyone. So this is the price for Monte Carlo simulation. Computer. So it's a cheap price nowadays. And we can take a super advantage of that. You're going to be requested to do Monte Carlo simulation in the homework. I will discuss the details tomorrow, but that's super intuitive. Is modeling, and we can learn and that. Questions, guys? Just one last thing for tomorrow, and we will wrap up the chapter 2. For tomorrow, we're going to apply this theory that we have discussed, right? Valuation. And I want to show you, I want to present the value of something important. Still using our favorite approach, which is the risk-adjusted approach. So this thing, right? No risk neutral. We are not going to deal with derivatives in this course. I want to use the standard approach, and I'm going to present you to something that everyone does every day. So imagine that you have a contract. Someone says, I'm going to pay you to the bank. I'm going to give you, according to a calendar, those payments. 350,000, 550,000, blah, blah, blah. In this particular calendar. Now, how much is this worth today? Because you're a bank, this is an asset for you. An asset, something you are going to have in the asset side of the balance sheet. You want to put that with a value. How much is the value of this contract? And we can value that using the techniques that we have discussed. All what you need to do is discount those things to present using the risk-free rate plus premium. Okay, premium. Let's see that the bank says for this particular client, the premium is going to be 2% annual. But we need the risk-free rate. And then we will say, okay, but there is a single risk-free rate, right? And the answer is no. Surprise, surprise. It turns out that, as we said before, one thing is your life, the theoretical life, and which you typically assume a single risk-free rate. Most models have just a single rate. But when you go to real life, what you are presented is something like this. That was when I did this slide, September 15. So right now, if you check how the risk-free rate in the European Union looks like, we have something like this. Those are bonds issued with AAA denomination, so risk-free, that's what we wanted, but with different maturities. And in contrast to our theoretical models that assume a single risk-free rate, we have a curve, which is called the yield curve. This is called the yield curve. Now, how can we use that? It's like Tommaso, Jude, and I see you. I see you tomorrow.
Se debe poder descargar una base de datos con los GIOs, ¿no? Se debe poder descargar una base de datos con los GIOs.
Lo que es más larga.
No puedes cerrar,
El libro de ayer,
Oye,